Welcome to the exciting journey of machine vision, a multifaceted domain that integrates the principles of computer science, engineering, and physics to enable machines to interpret and interact with the visual environment. This course is meticulously designed to introduce students to the intricate processes that underlie the generation of symbolic descriptions of the environment from images. Our exploration will encompass a wide range of topics, each building upon the last to foster a comprehensive understanding of machine vision. 1. Overview and image formation. We begin our journey with a fundamental overview of image formation, addressing key questions. Where will the image form? How bright will it be? What methods can we use to invert the image formation process? Through this foundational understanding, students will gain insight into the basic principles of optical systems and image capturing, laying the groundwork for further exploration. 2. Physics of image formation. As we delve deeper, we will explore the physics governing image formation, focusing on concepts such as perspective projection and the time derivative associated with motion fields. Understanding how light interacts with objects and how images are projected onto sensors will be crucial as we push into more advanced topics. 3. Time to contact and focus of expansion. In the following lectures, we will examine fundamental concepts like time to contact and the focus of expansion. These principles are vital for understanding how machines perceive motion and distance. Through direct motion vision methods, we will gain insights into how machines can utilize these concepts to navigate their environment effectively. 4. Optical flow and camera calibration. Next, we will explore fixed optical flow and discuss applications such as optical mice. Students will learn about the constant brightness assumption, which simplifies many image processing tasks, and closed-form solutions that can be implemented in real-time applications. Additionally, we will demonstrate the significance of vanishing points in camera calibration, enhancing student skills to calibrate visual systems accurately. 5. Photometric stereo. The course will introduce students to photometric stereo techniques, discussing noise gain, error amplification, and reviewing eigenvalues and eigenvectors. Students will apply this knowledge to enhance image quality and extract valuable information about shapes and surfaces. 6. Gradient space and reflectance mapping. As we transition into gradient space, we will study the reflectance map and the image irradiance equation, highlighting the importance of mnemonic projection in image analysis. Understanding these concepts will allow students to reconstruct 3D shapes from 2D images effectively. 7. Shape from shading. In our discussions about shape from shading, we will analyze special cases, such as those in lunar surfaces and scanning electron microscopes. We will also employ Green's theorem in photometric stereo contexts to illustrate the mathematical foundations of shape recovery. 8. Addressing nonlinear PDEs. Moving forward, we will tackle the general case of shape from shading, transforming our understanding from first-order nonlinear partial differential equations to a system of 5 ordinary differential equations. This segment will highlight the complexity of interpreting visual information and recovering shapes from ambiguous images. 9. Edge detection and subpixel measurements. The course will include a critical examination of edge detection techniques, assessing subpixel position, and introducing students to advanced algorithms like Cortic for line detection. The importance of edge detection in identifying object boundaries will be emphasized through practical applications. 10. Binary image processing and blob analysis. We will cover binary image processing in detail, exploring methods for blob analysis, and discussing how to apply Green's theorem in this context. Students will learn about derivative and integral as convolutions, key concepts that support robust image processing methodologies. 11. Object detection and pose determination. Our focus will then shift to object detection, recognition, and pose determination techniques. We will utilize methods such as PatQuick, a patented algorithm that enhances object detection efficiency and accuracy in various environments. 12. Advanced inspection techniques. Continuing on this path, we will examine inspection techniques in PatQuick and introduce students to the Hoff transform and homography. These methods are critical for position determination and multi-scale analysis of visual scenes. 13. Recognition and filtering techniques. We'll dive into alignment and recognition processes in PatMax, exploring concepts such as distance fields, filtering, and subsampling techniques. Understanding these methods will enable students to develop systems capable of precise object recognition across diverse scenarios. 14. Fast convolution and filtering. The course emphasizes the importance of fast convolution, low-pass filter approximations, and integral images, focusing on patents that provide insights into cutting-edge techniques in image processing. Developing an understanding of these concepts is essential for efficient real-time visual processing. 15. Photogrammetry and 3D orientation. A significant portion of the course will be dedicated to photogrammetry, where students will learn about orientation techniques, axes of inertia, and symmetry involved in reconstructing 3D environments from 2D images. We will touch upon both absolute and relative orientations, providing a robust framework for understanding spatial relationships in imaging. 16. Rotation representation. We will explore how to represent rotation using unit quaternions and delve into the space of rotations. This mathematical foundation is critical for understanding how to manipulate and interpret images in dynamic environments. 17. Absolute orientation and outlier robustness. In the later stages of the course, we will focus on achieving absolute orientation in closed form, dealing with outliers, and emphasizing robustness in visual processing through methods like RANSAC. This knowledge will prepare students for real-world challenges where data might be imperfect. 18. Structure for motion and camera calibration. We will discuss relative orientation, binocular stereo, and structure for motion techniques. Students will engage in practical applications, gaining experience in camera calibration and reprojecting images accurately across different dimensions. 19. Advanced image representation. As we move towards summarizing our knowledge, we will introduce concepts like the Gaussian image and extended Gaussian image along with solids of revolution and direction histograms. These advanced representations will enable students to understand complex geometrical relationships in images better. 20. Integration of concepts. Finally, we will focus on integrating all these concepts, tying together the diverse strands of knowledge acquired throughout the course. The culmination of our journey will involve putting everything into practice and enabling students to appreciate the intricacies of machine vision fully. Conclusion and invitation. To conclude this extensive exploration, I invite you to stay connected by following the ECL Center's Telegram channel for timely updates regarding the upcoming exam, which is set for April 3, 2025. The exam will be available online, free of charge, and open to the public. It's an excellent opportunity to challenge yourself and apply the knowledge you've gained. Thank you for embarking on this journey into machine vision with us.